Okay, from all the topics you sent me on the list, I think the next one in importance and difficulty, like the most difficult one after related rates or implicit differentiation, is optimization. Mostly because it's always word problems. Each problem, once again, it's very similar to related rates because it involves a lot of formulas from geometry and Pythagorean theorem, or maybe the distance formula, depending on what type of example they give you. There's like a pretty much infinite number of different formulas or problems that you can get, and that makes it hard. However, they usually stick to very similar ones. If you have any specific problems involving optimization that you want me to do, send a picture, because right now I'm going to be using the ones in my textbook, and I do think they're a little bit hard, but they do some that are very important, so I'm still going to go ahead and do all of these. So first, let me explain what optimization is. So if you have any relationship that can be represented with a curve, maybe a parabola, maybe. If you were to graph it and I were to ask you, okay, so what is the maximum point, you would directly know it's the vertex. So what we're going to be doing is we're going to be writing an equation that would be the equation you would graph, and it's always going to be a curve. And then you, instead of graphing it to find the maximum point, we would first find your equation that you would graph, but we're not going to graph it. Then you would find its derivative, which is the slope of the tangent line all the way around. Then you make it equal to 0, and then you solve. If it's a parabola, or if you only got one maximum or minimum value, you automatically know that that would be your vertex. However, your graph could possibly look like this. And you could have many maximums, or if you were maximizing or minimums, you could have many different points where the derivative is 0. And in that specific case where you get more than one possibility, you would have to try them all out one by one into the original function to see which one would give you either the maximum value if you're trying to maximize something, or the minimum value if you were trying to minimize something. So you would have to do some trial and error. So that doesn't seem hard. You just have to write an equation, derive it, and then make it equal to 0 and solve. What makes it harder? It makes it harder that very frequently you're going to have too many variables. For example, imagine it was a formula that uses the volume of a triangular prism is 1/3 area of the base times height of the prism. Okay, so you have two variables. You end up having 3 variables. The one you would be deriving in terms of, and 2 over here. You're not allowed to have 2 variables. So this is where it's going to get a little bit tricky. They're going to give you an additional equation, whether they're going to tell it to you in the sentence form, or sometimes you would have to do proportions if they're similar triangles. Sometimes you need to figure it out, deduce it, or sometimes it's really obvious that relates these 2 variables on the right side of the equation. For example, in this specific example, they could say something like the height is always half of the base or something. And then you're going to be doing substitution to substitute for one of the variables. You sometimes have freedom to decide which one you're going to be substituting for. And at the very end, once you only have, in this case, I would substitute the height for 1/2 of the base. This example, I made it up. And then you would simplify that. Once you only have one variable on the right side of your function, obviously you have a different variable on the left, which is the one you're deriving, then you would just find the derivative, make it equal to 0, and solve. So it's the preparing or the prepping it that it makes it a little bit harder, because you're going to have to very frequently use, sometimes it's only one, when there's only one variable over here. But if there's 2 variables, you would need an additional relationship to substitute, and those are the hard problems. So let's identify from the examples I have over here how to figure out the formulas you're going to be using in each example, and how to figure out if there's an additional equation or relationship that you need, or if one is going to be enough. Okay, so let's look at example 1. I wish I had cut these shorter, but aquí los tengo. Estamos bien. dice. Ahí lo voy a hacer ahorita para tener más espacio. I'm going to leave the answer. Quiero dejar el dibujo. Okay, sorry about that. There we go. Okay, that's better. Okay, so for example 1, it reads, a manufacturer wants to design an open box having a square base and a surface area of 108 square inches, as shown in figure 5.51. What dimensions would produce a box with the maximum volume? So first, let's identify the formula we're going to be optimizing. And the formula you're going to be optimizing is the one that they ask you, maximum volume. So it's going to be the volume formula. And if you look at the dimensions of this box, the volume of that box would be x times h times h. Area of the base, which is x, times the height, which is h. So right there, we have two variables on the right side, and I can't have that. So I know I need an additional relationship to substitute. So which relationship am I going to use? They usually give you a hint in the problem, and they talk about a different relationship, and they say the surface area of 108 square inches. So what's the formula for surface area of this specific box? So if you notice, we have 2x squared, which is the bottom and the top. Oh, it doesn't have a top. So it's an open box. So we only have one. The surface area of this is only going to be, the bottom is x squared. And we have 4 lateral faces, which are x times h. So it's plus 4x times h. And they give me the surface area to be 108. So I make 108 equals x squared plus 4xh. So which variable do you think it's going to be easier for me to solve for in this relationship? Obviously, h is going to be much easier. So let's go ahead and do that. First, I'm going to do 108. Este pasa restando, so minus x squared equals 4xh. And then I want to leave h alone because it's the one I'm going to be substituting for. So this 4x pasa dividiendo este lado. So now that I have that h is equal to this, I can go to the main equation and substitute for h in there. So I'm going to get volume equals x squared times 108 minus x squared over 4x. Okay, then the next step here is to, now I only have one variable, so I'm good to optimize now. This would be an easier problem if I started right there. However, let's go ahead and make this problem easier by simplifying the equation before I derive it. So let me distribute that x squared to the top. So it's 108x squared minus x to the 4. And I'm going to individually divide them by 4x. And that's 108 divided by 4. That's 27. X minus, that's 1/4 x cubed. Okay, so that's my formula for volume. To optimize my volume, I need to figure out where it has a horizontal tangent line or where it has a maximum or a minimum. So the first thing what I'm doing is I'm going to be deriving this to find the derivative of the volume. Don't forget always to derive in optimization problems. So the derivative of 27x is just 27 minus the derivative of that, bring down the 3, subtract 1. That's my derivative. I make it equal to 0, and then I solve. (27) over to the other side. So 27 divided by 3/4. So So I times 4/3. So I solve for x by doing, don't forget when you have a second power, it's positive or negative square root of 36, which is positive or negative 6. So those are my two answers to that equation. However, remember, x is the side of a square, and a square cannot have a negative side. So the negative 6 doesn't make any sense. So the answer is 6, and let me go back and find the units. It would be 6, and we're talking about the length, which is 6 square inches. What dimensions will produce a box with maximum volume? So I already found the value, the value that would make x, the value of x that would have the maximum volume. However, the dimensions are x and h. So I need to now also find h, but I do have that equation where I related them, where I related directly h to x. Where is that? ¿Qué lo hice? Over here. Era este. Lo borré sin querer un poquito. Era este de acá. So now that I know that x is 6, I can plug it into this equation over here to find the value of h. And that's 108 minus 6 squared, which is 36, divided by 4 times 6. That's 3. So the dimensions that would produce the largest box in this specific example are 6, I believe it was inches. Yes, 6 inches times 6 inches times 3 inches. Right there. Okay, let me look at the next example. So that was an easy no, not an easy. I would say it was medium difficulty level. The reason why the formulas were easy, but I did need to have a second relationship to solve for h and substitute it back in. Okay, now let's look at this one. Finding the minimum distance. Which point, okay, this is a very common problem. Wherever they want you to find the minimum distance between an equation and a random point. And if you have no idea how to do it, it would be that kind of problem that you think is like extremely hard or critical thinking, but the process is very set forward. You already know what you're supposed to do if you're prepared. Okay, so the graph they're giving me, so the relationship between y and x is y equals 4 minus x squared. Oh, that's a 2, sorry. Me sale como un 5. However, they don't want me to maximize or minimize the relationship. They're not asking me, oh, what is the maximum point for this equation? They want me to find the closest point, which point on this graph is closest to the point 0, 2. So how do you find the distance between a point and a curve? How do you find the distance between 2 points? You use the distance formula, okay? And the distance formula is the square root of x2 minus x1 squared, y2 minus y1 squared. So let's use for x1 and y1, let's just leave them, we're going to be using the point because those are the values of one of the point we know for sure. And for the other one, which is the unknown point, I'm going to leave the variables, which is x2. So it's going to look like this. This is always how it looks like. X minus 0 squared. I'm substituting for the point for x1 and y1. And y minus 2 squared. Okay? And this looks like x squared plus y minus 2 squared. So that is the distance formula written for this specific point. Now, I have 2 variables, and I can't have that. I need to solve for one of them. That is the reason why they give me the other relationship of the function, because that's the relationship where that point will fall. So I already have y alone here, so it's not that bad. I'm going to be substituting that y value in there, and I'm going to get a distance of the square root of x squared plus, so instead of y, 4 minus x squared minus 2 squared. Okay, so now let us simplify that inside part by doing some basic algebra right there. Let me FOIL that now. You follow along. 4 minus 4x squared plus x to the 4. And now let me combine like terms. X to the 4 minus 3x squared plus 4. So that's my distance formula with only one variable. So that right there is what I'm going to have to derive. Okay, how do I derive that with respect to x? I am going to be rewriting it first as x to the 4 minus 3x squared plus 4 to the 1/2. Then I am going to be using the chain rule. So the derivative of d with respect to x, I'm going to call it d prime. Just shorthand. Este baja para acá. I subtract 1. And then I multiply times, I'm using the chain rule, so now I need to multiply this times the derivative of the inside part, which is 4x cubed minus 6x. Ooh, okay. So now that's my answer for my derivative. Let me write it in a simpler way so that you can see how you're going to make that equal to 0. So I'm going to put the 1/2 like this. The negative exponent in that parentheses means it goes in the denominator, so that's x4 minus 3x squared plus 4 to the negative 1/2. Sorry, to the 1/2 porque ya lo pasé para abajo. Positive 1/2 because I sent it to the bottom, and then the other parenthesis stays on the top. I'm going to go ahead and factor that parenthesis because it's got greatest common factor of 2x. And that's going to be, ese 1. 2x, and that's going to be 2x squared minus 3. Boom. Okay, so that's my derivative right there. Simplify that 2 cancels out with that 2, but that's it. Now, how do I make that equal to 0? It looks like it's going to be horrible. Whenever you have a rational function, so you have x on the top and x on the bottom, and it's equal to 0, keep in mind that the bottom can never be 0. So the only way this can be 0 is if the top is 0. So you focus on the top. So you got two choices. X could be 0 or 2. You make this equal to 0 and that equal to 0, and you got 2x squared equals 3. So x would be the positive or negative square root of 3 over 2. Okay, so those are my three possibilities actually. Let me go back and see how they did this in the study. Okay, so we have 3 possible choices for the x value of the closest point. So there's many different ways you could figure out which of these would give you the closest point. The first is for every, I'm going to show you how to do it, but I'm not going to do it because that would take extremely long. The first thing you would do is you would find for each one of these 3 values, you would find the corresponding y value by plugging the x value into the relationship equation that they gave us. Esta. Okay, let me bring it down. Okay. You would plug each one of these individually into this equation to find the corresponding y values, and then once you have those x and y values for each of those 3 points, you would plug them into the distance formula over here. Sorry about the mess, pero es la manera de hacerlo acá. Una vez que tenés esos puntos, how do I cut this? No, espérame, déjame hacer eso mejor. Okay, you would plug them into the distance formula to see which one would give you the shortest distance. That's one way to do it. A bit time consuming, I guess. In the book, what they did is they made a, like you did for the first derivative test, they made a number line where they included the negative square root of 3 over 2, the 0, and the positive square root of 3 over 2. And they took values in each of the intervals and plugged them into the derivative we got and see which were like positive or negative. I'm not sure this was it, but and then they would say if it was increasing or decreasing, and they would decide if it was a maximum or a minimum based on that. I would not go there. I would just do whatever my reasoning tells me, which is just to find all three possible answers for y, get all three possible points, and plug them into the distance formula to see which one gives you the smallest answer. So whenever you have a whole bunch of answers, it's like you had a list of possible candidates that could be your result, and you need to test all of them to see which one gives you either the maximum or the minimum value. In this case, it was the minimum value. Go ahead and do that, and you should get that your answer is both positive square root of 3 over 2 and negative square root of 3 over 2 actually yield the same distance because it's a parabola. Okay, now let me do an additional example. Okay. I like the geometry examples a lot, so let's see how this looks. A rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inch, and the margins on the left and the right are to be 1 inch. This is a very common problem. What should be the dimensions of the page so that the least amount of paper is used? Amount of paper is area. So they want me to minimize the area of the big page. So first we need to establish what my variable, well, they already did it here in the diagram. Imagine they didn't give you a diagram. Let's go a little bit further. Imagine they didn't give you the diagram. Let's focus right now only on the problem. Así. You would have to draw it, and you would have to figure out what it is that they want you to do. So what you have is a large piece of paper with an area of print in here. And I believe they used, I want to use their same so we don't get confused with when we're checking. Give me a second. They used X as, aquí lo tengo. X was the height and Y was the width. So X was esta dimensión de acá adentro y Y era este acá. Okay, so they told us also that at the top and bottom we have 1.5 extra inches. So this distance right here is 1.5, and this in the bottom is 1.5. So the whole page, if you notice, is X plus 1.5 at the top plus 1.5 at the bottom. So that's X plus 3. You need to add both margins to X. And Y, which is the width, you need to add the margins on the left and right, which are 1 inches each. So that's Y plus 2. So the whole page is the area printed, which is X and Y, but we have to add the margins. So the entire page is X plus 3 and Y plus 2. So now you can find the equation you're going to be using for the area of the page. So the area is X plus 3 and Y plus 2. So we have an issue here because we have two variables on the right side. So there has to be an additional relationship. There it is. the printed area, the area of print, which is just the center part over here, which is just x times y, is equal to 24 square inches. So I have my relationship. You get to pick here. You can either solve for x or solve for y. Let's do what they did. They substituted for y. So y equals 24 over x. Pasan el x dividing there. And then you substitute that y in there. So that would be area equals x plus 3 times 24 over x plus 2. Then you would FOIL that. X times 24 over x is just 24. X to x plus 3 times 24 over x is 3 times 24, 72 over x, which is 72x to the negative 1. I'm just going to write it that because it's going to be easier to derive. And 3 times 2 is 6. I'm going to add the 6 to the 24. And then I am going to derive. Oops, sorry about that. The derivative of 30 is 0. The derivative of 2x is 2. The derivative of that is negative 72x to the negative 2. And then I make that equal to 0 and I solve. How do I solve this? Okay, I'm going to take that 2 over to the other, no, the 72x to negative 2 over to the other side. And then I multiply both sides times x squared just to get rid of that x to negative 2, and that gives me 2x squared equals 72. Because that times that is x to the 0, which is just 1, divided by 2. And once again, I get x equals positive or negative square root of 36, which is 6. I can't have a negative dimension, so my answer is positive 6, and I only have one possible. So when it's like straightforward, only one, that's going to be your answer. You don't even need to consider it. So that's the value of x. However, they probably want me both. They probably are asking for both dimensions. Let's go back and look at the question. It's very important that you always answer the correct question. The question is, what should the dimensions of the page, the entire page? I only found x. The dimensions of the entire page were x plus 3 and y plus 2. And x times y is 24. So using those relationships, I can deduce that y is going to be 4. Sorry. Esto es viejo también, no sé qué hacer. Continue over here, sorry about that. So since x times y were 24, I can deduce that y right here is going to be 4. And the dimensions were x plus 3 and y plus 2. So it's 9 and 6. And I believe it was inches or centimeters, so keep in mind always to use the correct unit. Okay, it was inches. Okay, and there they are. Okay. So those are very, very, very basic optimization problems. I think this is about the difficulty level you would expect in your AP, the one we just did. Let me see if there's another one over here that's worth doing right now. 2 posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. They're to be stayed by 2 wires attached to a single stake, running from ground level to the top of each post. Where should the stake be placed to use the least amount of wire? So the wire is y plus z. Y plus z. Yes, because the wire is this one and this one. Okay. So the first thing I need to do is you have right triangles. Whenever you have right triangles and you're talking about their lengths, you're either always going to be using the Pythagorean theorem or SOHCAHTOA. right here, I think it's pretty obvious that we're going to be using Pythagorean theorem to relate the length that we know to the length that we don't know. Let's go ahead and see. I'm not even sure the path this specific problem is going to take, but I need to have a feel at it. So I'm always going to start with what I know. Well, 12 squared plus x squared equals y squared. That's the first relationship. And the second relationship is 28 squared plus 30 minus x squared equals z squared. And what do I need to minimize? I need to minimize y plus z. Okay. So pretty much what they did here, in order to save space, I'm going to walk you through the easy steps over on the right over here. So the first thing they did is they solved for y and for z in each equation by taking that second power and doing the square root of the sides, and you get this over here, okay? And the wire, which is we want to minimize, is y plus z. So they established that right there. So now what they did is they took y plus z, which is the amount of wire, and they substituted y for what y is equal to, and they substituted z for what z is equal to, and they got this. And we know that x has to be less than 30 because they are 30 feet apart. Okay, so x cannot be greater than 30 if they're only, that makes no logical sense. So now once you have that right there, you're going to be deriving it. Okay, how do we derive that equation? Let me erase everything to work on the derivative. You would do x squared plus 144 to the 1/2 plus parentheses x squared minus 60x plus 1648 1684, sorry, to the 1/2. Okay, so now I would bring down the 1/2, dejo lo de adentro igual, chain rule. I subtract 1, and then I multiply times the derivative of the inside part. And that's where you get this over here. And then you do the same thing over here. You bring down the 1/2, you leave the inside part the same, you subtract 1 from the exponent, and you multiply times the derivative of the inside part, and you get that. Now you make that equal to 0, and this part over here is what you will use your TI. I'm sure they would not expect you to do this specific part by hand. So you just take this equation, you plug it into your TI into F to solve. I think you do know how to use that. And you would find two x values, 9 and negative 22.5. You can't have a negative amount of wire. So you know your answer is going to be 9 because the other one's not part of the domain. Now once you already have the answer for x, you can easily replace to find the value of y by using this equation over here. Okay, go ahead and do that and make sure you can get the result stated over here. So x is 9, so you're putting it 9 feet from the 12-foot pole. Okay, any questions on optimization problems?